Hello, students. In this video, we're going to kick off week 2 talking about essentially atoms and elements. So when you think of an element, you can think of one type of atom. So atom is the singular of element. So if I have a copper pipe, like a pure copper pipe, that would just be a bunch of copper atoms lined up together to make that element. So the element is the plural. So in this particular video, I'm going to talk about the basic atomic structure and the numbers that we see on the periodic table. So I'll talk about subatomic particles as well. What I'd like to do is I'm going to go ahead and share my screen, but before I do that, I'm going to turn off my video. And when I share my screen, there won't be so much distraction. And if I actually write on the board, it won't shake. So the first thing is atomic number and mass number. So here I have a picture of a periodic table. And as discussed in the elemental symbol video, we see that the chemical symbol is there to help us identify what type of element it is and the name. Okay, and as we saw in that video, typically it's either the first letter capitalized or the first letter capitalized and the second letter lowercase, or sometimes the third. Now, the number that identifies the element is how the periodic table is organized. So the first element is hydrogen, and it has an atomic number, and that's what this is, of 1. Essentially, your atomic number, it's really simple. It's just the number of protons. So that's what I want you to know. And then when you look at the periodic table, we see that the atomic number is increasing. So the second element has 2 protons because it's an atomic number of 2. Helium, lithium has 3 protons, beryllium has 4, and so on and so on. So essentially, the atom is identified by the number of protons. It's the number of protons that dictates what the element is. So a helium has 2 protons. If I have something other than 2 protons, I would not be considered the helium atom. So for example, aluminum has 13 protons. Why is that? Well, if we look at aluminum on the periodic table, we see its atomic number is 13, and that's because it has 13 protons found in the nucleus. So we use the atomic number to identify the element. So it's specific for every element. It's the same for all the atoms of that element. So it doesn't matter what atom it is, it's going to have the same number of protons as all the other atoms in that element. So for sodium, every sodium atom has an atomic number of 11. That's what makes it sodium, and it has 11 protons. So the atomic number is equal to the number of protons, and it's typically above the symbol in the periodic table. So again, if we look at our basic understanding, we see that carbon has an atomic number of 6, so that means it has 6 protons. Lithium has an atomic number of 3. It has 3 protons. That's why lithium is in the 3rd position of the periodic table, and carbon is in the 6th position, because it's organized based on atomic number and the number of protons. We also see in our models here that there are other additional subatomic particles. So for lithiums, the 3 protons are in red, and they're found in the nucleus. But we also see that electrons are in blue, and they're outside the nucleus. And we also notice that if I have 3 protons, which are positively charged, if I want a neutral atom of lithium, I need the same number of electrons, because a 3 positive can only be a neutral atom if I would have 3 negatives. So what I notice is this atom has 3 electrons surrounding the nucleus because there's 3 protons in the nucleus. There is another subatomic particle, that's the neutron, and the neutron is neutral and has no charge and doesn't affect the charge of the atom. Now, it does contribute to the mass, and we'll talk about that in the upcoming slides. If we look at this particular atom of lithium, we see that there are 1, 2, 3, 4 neutrons. If we go to carbon 6, the reason why this is Carbon, is there 6 protons, 6 plus charges? Where are they? They're in our nucleus. 1, 2, 3, 4, 5, 6. So to have a neutral atom, I would need 6 electrons because, a positive 6 minus 6 would make a neutral atom. So I have 6 electrons. And where do I see the electrons? Outside the nucleus, surrounding, right? And in the nucleus, what also contributes to the mass are the neutrons, not just the protons. So I also see that in this particular atom of carbon, there's 1, 2, 3, 4, 5, 6 neutrons, okay? So the basic atomic structure is you have a really dense nucleus, and that's where all your protons and neutrons are. And in that dense nucleus is the majority of your mass, okay? Outside of the nucleus is where the electrons are being occupied. Now, we've seen the different models. So we first talked about Dalton's atomic theory in the video, where we believed that it was a solid sphere. We weren't too well aware. We knew it was neutral, and we knew the law of conservation of mass, but we didn't know that there were subatomic particles with different charges until Thomson came on the scene and discovered the electron. So Thomson came up with the, plum pudding model, which I like to refer to as the chocolate chip cookie model. And then Rutherford went on to further discover that there was a dense nucleus with the nuclear model, just as was stated in that video. So in these examples we're showing here are the nuclear models. But now when we look at the atom, we know that there's protons and neutrons in the nucleus and the electrons outside of the nucleus. We also know that the number of protons identifies the elements, and it's also referred to as the atomic number. But now we want to put everything in terms of mass. So when we talk about subatomic particles, an atomic mass unit is basically defined as 1/12 of the mass of carbon-12. So what do I mean by carbon-12? Carbon-12, if I write that down, I could write 612. If you remember, the 6 represented the atomic number, which was the number of protons. The 12 represents the atomic mass, or really what we can say is, what's a little more accurate is the mass number. And the mass number just equals the number of protons plus the number of neutrons. And we saw that in the nucleus. So in carbon's nucleus, there were 6 protons, 6 neutrons. You divide carbon-12 by 12, and you get roughly 1.66053,873 times 10 to the negative 27 kilograms, or roughly 1.66 times 10 to the negative 24 grams. Now that atomic mass unit is really small. It's not very practical. That's why later we discuss the concept of the mole, where we change that average atomic mass in the periodic table instead of atomic mass units into grams, because 1 gram has 6.022 times 10 to the 23rd atomic mass units, which is roughly that weight. But basically a proton has 1 AMU, and it's a lot easier to just say 1 AMU because this is a mouthful. This is a lot to say. So we just say a proton is roughly 1 AMU. A neutron is roughly 1 atomic mass unit, which again, that mass is really small, 1.66 times 10 to the negative 24 grams, or 10 to the negative 27 kilograms. Now, an electron is extremely small. In fact, it's not even an AMU. It's 0.000549 AMU, which is roughly 1,821st AMU. Now, how did I get that number, right? How did I get that number? I just divide 1 by this number. So if I did take 1 and divide it by 0.000549, I'll get roughly 1,821. So an electron is roughly 2,000 of an AMU, so it really doesn't contribute to the mass that much as the neutrons and protons. So we typically don't consider that mass as, contributing. It's negligible. So when we look at the particles in the atom, I basically want you to understand this table. We have 3 subatomic particles: protons, neutrons, and electrons. Protons are positively charged. That's why you have the superscript positive. Neutrons are neutral. That's why you have the superscript of a 0. And electrons are negative, and that's why we have a negative sign for a superscript. The AMU, it's roughly 1 for a proton, roughly 1 for a neutron, but for electrons, it's so small, it's negligible. Now, some people might say, well, why is it negligible? You can think of it as if I had an elephant that's being weighed by the ton, 2,000 pounds, and it jumps on a scale and it weighs 4 tons. If I throw a flea on its back, it's not going to change the scale at all that's measuring in tons, because that flea's mass is insignificant. So, or negligible is a better word. So that's kind of the situation with electrons. When we're actually looking at masses, we're pretty much looking at protons and neutrons, because electrons are so far down on the significant figures placement value. The other thing that you need to know is the location of the subatomic particle. And the big thing is, again, as Rutherford discovered with his gold foil experiment, is the dense nucleus, where the majority of the mass is where you find your protons and neutrons, because they're roughly 1 AMU. And outside of the nucleus are your electrons. So the mass number is the bigger number. The atomic number is just the number of protons. And the mass number is equal to the number of protons plus the number of neutrons. And that's because they both are 1 AMU. So the element hydrogen, elemental symbol H, atomic number 1. The mass number is 1. So what does that mean? Well, if the atomic number is 1, I have 1 proton. If the mass number is the number of protons and neutrons, right, and it's only 1, well, that must mean there's no neutrons. For it to be neutral, I have to have 1 electron. So you can think of it as I have 1 proton in the nucleus, and there is 1 electron orbiting it. So the positive and negative charge cancel out, and I have a neutral atom. So if I see nitrogen, the atomic number, if I look at a periodic table, is 7. If the mass number is 14, right, that means I have 7 protons, but I must also have 7 neutrons. And why is that? 7 plus 7 equals 14, my mass number. Because again, this is the number of protons. This is the number of neutrons. When I add that up, it equals a mass number. Just like 1 plus 0 is 1. If I go to chlorine and I see that the atomic number is 17 and the mass number is 35, well, what does that mean? There must be 17 protons, but what adds up to 35? 18. So I actually have 18 neutrons. But then I notice, well, wait a second. I can have a situation where the mass number for chlorine is 37. So to be chlorine, right, the identity of the element is the number of protons in the nucleus. And we've already established that that's your atomic number. So I know there's 17 protons. So why is the mass different? Well, the mass is also the number of neutrons. So 17 plus 20 neutrons adds up to a mass number of 37. So at this point, you might be asking, well, how is it possible that I have 2 chlorine atoms with different masses? And that's an excellent question. They're both chlorine because their atomic number is 17 and they have 17 protons. That was the whole purpose of this video, was to show you that you use the atomic number, the number of protons, to identify the element. However, what we do notice, the reason why their masses are different is they have different numbers of neutrons. And they have different number of neutrons because they are isotopes. And that is what we'll talk about in our next video, is how can we identify isotopes and how can we actually calculate what we see on the periodic table as not a mass number, but an average atomic mass. Because if you look on the periodic table, chlorine is definitely 17, showing that there are 17 protons, and that's why it's chlorine. But the average atomic mass is 35.45 AMU. And our isotope video is the next one that will explain that. So thanks for watching, and I look forward to seeing you in the next video.